You ready? Hey, Sierra. Are you guys ready? Okay. A couple things I want to mention to you. We start with this slide every day. A version of it. It has a different outline every day. But the SI schedule over here is the same every day. And so are the office hours. I had a student text me or message me in web courses the other day. Dr. B, can I come to your office hour? And it was Monday. I said, no. Office hours are Wednesdays. And it's right up here every day. You just guys skip over it. But yeah, that's the scoop. A couple things. Tuesday coming up, 5 days from today, October 1-6 is exam 2. Now we have the same procedures as before. No cell phones may be used. Scantron, iClicker, pencil, eraser, calculator are fine. You'll write your name on the exam and your PID. Hey, you guys, bring your ID cards so you don't mess up your PID, because there's a bunch of people that messed up their PIDs last time, and a couple students forgot to bubble in exam form A, B, C, or D. And when you do that, it kind of throws a wrench in the works and causes a little bit of extra work for everybody. So just remember to do that, and do not get caught napping. But yeah, bring your ID card, and if you forget your PID, you can just look it up on that. It's the UCF ID number. The Scantron has a space for a letter, but you don't have to type that. You don't have to bubble the letter in anymore. The SI schedule. Now, Maria told me on Tuesday that she's not having the extended afternoon session. She's just having a regular 3:30 to 4:20 session. So it's not going to go till 5 o'clock, but it will go to 4:20. So get your you-know-what over there if you can, Damien, and get some study time in with Maria. If you can squeeze it into your lecture, into your schedule. If you can't, you can't. My suggestion to everybody is to find a human in this class or the other class that is reasonably friendly and study with them. And even if neither of you did spectacular on exam 1, you can still, iron sharpens iron, the saying goes. So having one other person. Now, if you come to office hours on Wednesdays, you study with me. You go to SI, you study with Maria and everybody else that's there. And hopefully make a friend at SI that you can study with later on Monday night. So I heartily recommend that. It's always the good thing to do. Now, as far as topics for exam 2, we'll just do a little rundown on topics here. So 3.5, chapter 3.5, uniform circular motion. Yeah, we did that. That's going to be on this exam. We kind of skipped over it before exam 1, but we got it first thing after exam 1. Chapter 3.8 to 3.13, universal gravitation, the gravitational interaction. There's a ton of stuff on this exam. I mean, we're going to have, calculations. It'll be a similar format. But except I might have 3 or 4 iClicker items. And usually the iClicker items will include some serious calculations. You know, there'll be a couple cinchy calculations that you can do in your Coconut on the multiple choice part, the Scantron part. You know, so I'll have the right answer and you just got to select it A, B, C, D, or E. But then on the iClicker, you know, you might have to do a little bit more deluxe calculation. So I might have 3 or 4 items on the iClicker. So it might be, you know, like maybe 8 or 9 iClicker points. So that would be 41 or 42 Scantron dots. All right. But it'll be something like the last time. And gravitation is going to be in there. Now, we also talked about chapter 4, all of chapter 4. So that means, you know, the free fall energy levels that we had a talkie PDF on and we had a lot of lecture on. Boxcars and interactions, molecules, etc., etc. Chapter 5, which we're going to finish today, and we'll save chapter 6 for after exam 2. But chapter 5, so ice skater effect, etc., which we'll demonstrate up front here today in a few minutes. We'll get some volunteers from the audience. Somebody with relatively short hair and that they're not wearing a lot of jewelry or a scarf or anything, because we're going to be using a bicycle wheel up here. We don't want to get anything caught in the bicycle wheel. So my general advice is study everything. So lectures in YouTube lead the way. Your lecture notes are your study guide. Okay, that's why you take notes. But also don't forget the clicking questions in lecture. If they're in lecture, they're important enough for me to include in lecture. Therefore, they're important questions. Therefore, they might show up on exam 2. Or something like them might show up on exam 2. All right, so you just got to wait and see. Mini reviews in Great River Learning, GRL. Now, I understand that chapter 4 is running, and you're supposed to have like unlimited attempts. Who's had 5 attempts on chapter 4 mini review? Anybody? Nobody? Who's taken 4 attempts on one person? Okay, do you still have another attempt? Well, that's what I thought. Somebody told me on messaging last night that it was, they wouldn't let her take another attempt. Really? Okay, just keep clicking it. All right. Can you post a discussion thread about that in discussions? It'll probably help a bunch of people. Thanks for doing that. Okay. Now, before we get to mini reviews, or finish with that, I'm going to activate the Chapter 5 mini review. And it's not active right now, but I'm going to try to activate it after class. So maybe start looking for that, tonight or something like that. Question? Wait a minute. You're Katie, right? What? Bailey. Okay. Can you stand up? What is your name again? Rosie. Stand up, Rosie. Bailey, can you stand up? Bailey and Rosie. Rosie, I want you to give some advice to Bailey after class. Okay? On how to, yeah. Because it's supposed to work. It's supposed to be like infinity attempts. So, yeah. Well, you work it out with Rosie. Rosie, do you use your phone for the Great River? Oh, no. Laptop? Do you have your laptop with you? Do you have your Bailey? Do you have your laptop with you? Dude, no wonder you can't do any more attempts. Your laptop is dead. Not getting through to you guys. Anyways, go over to the library or something for 5 minutes and fart around with it. Homework and web courses. You're going to have a decent chunk of homework tonight, or maybe tomorrow, due Tuesday, at the beginning. Why? Because I love homework. Rachel, it's fine. You don't have to. Giving me the business from the cheap seats, it's fine. Anyway, there'll be some, because there's stuff in web courses, Rachel, the reason that you have homework in web courses, there's stuff that I can do there easily that I can't, is very difficult to do over in Great Rivers. So I'm not an expert on Great Rivers yet. So we have a talking PDF about the free fall energy levels table for a box of Doritos, I think it was. But you know the things you do with a box of Doritos, you're going to... Hi, Melissa. What is your name behind Melissa? What is your name again? No, don't look back behind her. You. Yeah. No, not you. Yeah. You were at office hours yesterday, right? What is your name again? Angelica. And what's your name back there? Yeah. Sweet. Okay, so Melissa and Angelica were both at office hours. Ashley, hopefully soon you'll be at office hours. But anyways, I wasn't trying, I'm practicing names, Ashley, so don't worry. Everything's fine. Yeah, what's your name?
My name is David. Is there a way to open like a grade calculator for this class?
No. Yes, there is a way. But you'd have to pay me $1 million first. Because I do not, what is your name again? David. David was asking, is there a way to open up the grading calculator in web courses? The answer is yes, but the thing about it is the way that the grading, and I've explained this a couple times already, the grading scheme that you can put, you cannot put a grading scheme in web courses as complex as ours. So in other words, like for instance, clicking, the 85% leeway level, there's no way to do that in web courses because my grade book in web courses is not a spreadsheet. In the old Blackboard system that we had, about 5-6 years ago, you could do that. You could link cells and stuff because it was a spreadsheet, but this one you can't. So the problem is they do a lot of stuff automatically for you guys, and I just post the stuff. I post the information that you guys need, and they just add it all up. Anything that I put in there, they just add it all up. And they give you some kind of percentage. And so a couple years ago, I had students that were saying, Dr. B, how come my grade for this class is 1,400%? Because Canvas just willy-nilly adds up everything and divides by how many. And so that's as complicated as their grade book is. But our grading scheme is much more complicated than that. And so I turn it off simply because I don't want people to, see those, 1,700%, grades and stuff because that's confusing. But it's also the reason that I go over grading examples in lecture, which we did a couple weeks ago, as I recall. So go back to the lecture where we did that example, and you'll be able to calculate your grade every time I post a clicking roundup. You can do everything. Okay, and I showed you how to do that. That proportion that you do for clicking points. If you're below 85%, if you're above 85%, just write in 25 out of 25. If you're below that, you got to do that little proportion and stuff, and then add that together. Homework, exams. So right now you could put 100 points officially on the books. 50 points for exam 1, 25 for homework, 25 for clicking. But our homework is not up yet because I haven't put the Chapter 2 mini review in there. Okay, you could, as soon as I get that up, you can have up-to-date homework. You know, so
Are all the mini reviews due by Tuesday? Like all 4?
3 and 4 and 5 will be due. Yeah, it's a study tool. They're not gigantic, but they'll be due Tuesday. Tuesday at 10:30 a.m. for you guys. Another place, you know, I was trying to get Bailey and Rosie to communicate here. Another place that you can communicate when you're not in the same room is discussions. Okay, so, and we've had some good discussions about various homework items, Ashley, this semester. So, you know, go into discussions and read what other people are saying, and you might pick up some tips. If somebody's in there, you know, help me with the equation for number 7 on homework 12, or, you know, whatever they're asking about, give them some tips. Don't give away the answer, but do give them some tips. And most of you have been doing that, so that's good. All right. Now, also for exam 2, special seating chart. All right. Now, listen carefully because our menu options have changed. Okay. So go ahead and jot this down. First row right up in front, empty. Nobody gets to sit there. Second and third row, Rosie, raise your hand. What is your name again? Alyssa and Rosie, raise your hands. Okay, those are the rows 2 and 3 up there. Every seat on those rows. Okay? And then rows 4 through 17. Okay, rowing team. First, right, raise your hand. Both of you guys raise your hand. Okay, that's row 4. And all the way back to you in the, no, not you. You in the, with the maroon top. Yeah, raise your hand. All the way, raise your hand. Stand up. She's kind of tiny. Okay, so all the way back to that back row, every other seat. Okay? So from rowing team to the very back. And the very back row, if some of you are all the way in the back row today, no. You're going to have to move forward. Today is okay if you want. All right? So, and we'll keep the back row. And the reason that we do that, as I've mentioned before, is so that I have pre-stacked packs of exams. I just hand them out row by row real fast, and then you guys get started real fast. Now, theoretically, it's a 1-hour test, 60 minutes. You had over that. You had 60-something minutes last time. And if we get the 9 o'clock lecture out of here by 10:20, and we could maybe get you guys started by 10:31. And then you'll have 79 minutes for the exam, which is what you want. A little bit more time for the exam, a little bit less stress for you. And there's stress enough. If there's a lot, you know, if you think about it, I was talking to students in office hours, there's a ton of different kinds of calculations that I can ask you about. So the clicker questions, you know, like the first test, the first section, and you guys had slightly different clicker questions, but exam 2, I can write completely different clicker questions and still have just a good clicking section. So just be very, very serious about it. Also, I forgot to ask this for the first hour. Raise your hand if you have, obviously everybody's here that's here, but if you have a friend or a roommate that had to take off just to go help their folks with the hurricane up in the Panhandle, go ahead and raise your hand if your friend or roommate or something had to take off. Nobody? Nobody in here knows somebody from the Panhandle? You do? Yeah. I had a couple. You did? Yeah. I had a couple students message me about it. I just was curious. So I guess raise your hand if your hometown is in Florida. Raise your hand. Okay. Raise your hand if your hometown is from Lake Okeechobee up to Ocala or Orlando. So most of you are from outside of. Raise your hand if your hometown is in Central Florida. See, okay, all right, that's good. All right. Thank God we didn't get it. All right, last time, let's get back down to business. We were talking about angular velocity. I'm going to ask you a clicker question in just a second. Have your clicker ready? Have your brain ready? We talked about the Orlando Eye. And we talked about the fact that if the wheel is spinning clockwise, which the Orlando Eye does spin clockwise, if you're to the west of it and you're looking east, the way this photo is, it spins that way, and so the angular velocity vector, what? I didn't hear it. I did? Hey. You know what it was? It was this, probably this. Anyway, I thought it was something that Axel did. He's out there clowning around in the aisle. Anyway, so the angular momentum and the angular velocity vector are into the plane of the screen. So the screen or the paper, if you're looking at a book, into. Now, go ahead and make a note. The opposite direction out of the screen toward you guys would be a circle with a dot in the middle of it to represent the tip of the arrow coming toward you. And this represents the feathers of the arrow going away from you. Okay, so now here's the other side. So here's the angular velocity arrow in yellow. And now you're kind of behind and a little bit to the side. And then down here's the right-hand rule. Now, when I was in grad school, I caught myself, I was working on some study notes, getting ready for a big exam, and it was one of these study guides where you can look up the answer in the back. And I was working on angular momentum or something, and I kept getting it wrong. If the answer was angular momentum to the left, I was getting angular momentum to the right, a minus sign. If the answer was up, I was getting down. And I kept thinking to myself, and so I asked my office mate, your grad student office, I'm working at and I asked my office mate, we're both studying for this big test. What am I doing wrong here? And and you know what it was? I was writing with my right hand, and I was using my left hand to figure out the right hand rule. So that's why everything came up backwards. So if I see you during the exam, I'm not going to look at anybody, okay? But if I see anybody in here, going like this with their left hand, I'll tell you, no, use your right hand, okay? And I've done that myself, so just try to remember that. I was writing with my right hand, using my left hand for the angular momentum vector. What a mess. All right, let's do a little clicker practice. And this is kind of a visual IQ test, so see if you can see the correct answer here. And we're on frequency DD, as you know. Question 1. Merry-go-round. So the sense of the merry-go-round is represented by the yellow arrow. So go ahead and vote for that. I see a lot of people going like this and going like this, and that's good. Good, Ashley. You're using the right. Okay, 15 seconds. Ten, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Okay, very good. Most of you got this correct. Up towards the sky is the correct answer. Majority of you got that. Now, here's how all you got to do is take your right hand, and see, I'm facing you guys, so it's a little bit easier for me, but it just, and your thumb points in the direction of the angular velocity or the angular momentum arrow. And hey, you guys, there's something, rotation, the motion, that you associate with rotation occurs in a plane. And a plane is 2 dimensions, x and y, for instance. But the arrow that represents that rotation as an angular velocity or an angular momentum is up out of the plane or down into the plane. So you have to think, the right-hand rule can be kind of challenging for that. And we'll have some more practice with that on homework, and you'll have probably a few questions of this kind on exam 2. So make a note of that. Now, I'm going to pause the YouTube right now. We're going to do some bicycle wheel demonstrations up front here to show you the angular momentum principles. So let me pause the YouTube. Okay, so the 2 bicycle wheel, or the 2 angular momentum demonstrations, the ice skater effect with Sierra, and with Joseph, the bicycle wheel demonstration. Now let's do some clicker questions. And I want you to read this one carefully. Now this one's about Sierra extending with the weights out or dipping the weights back in close. All right? So here's a question. Read it very carefully. Because this is the formula here for the moment of inertia of the student and the dumbbells. So the student's body, so Sierra, she didn't really move except for her arms. So all her MR squareds are over here in the first one. But the dumbbells, they definitely moved. So MR squared is definitely at issue over there. So what happens to MR squared of each dumbbell? Riddle me this, Batman. So, as always, talk with your neighbors. See if you can. I see some people in the back over here. They're going like this and like this. It's good. Good. Adam, this is something that your guys have to be intangible experts on for all the, because you guys do flips all the time, right? And you're controlling your rotation rate is critical. Whether you tuck or not, or whether you lay out. Do you do that? I mean, when you're doing, or do your teammates do that? Tuck and lay out and stuff? Different. Really? All right, 10 seconds to vote. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Okay, good. MR squared gets smaller, and most of you did answer that. All right, now, let's take some notes on the implications of that. So when you dip your arms inward, as Sierra did, the MR squared of each dumbbell gets smaller. So the moment of inertia, or the part of the moment of inertia tied to the dumbbells, got smaller. Now, her body moment of inertia was the same, all right? But the fraction of her total moment of inertia correlating to those hand weights did change. So let's work on that. So MR squared, when her arms are out, initially, time T equals T1, I1 is larger because the MR squareds are bigger out here, okay? You got an MR squared over here that's bigger, and you got an MR squared out here that's bigger. Plus you got her arm, but we'll forget about the arm for now, okay? Okay, we're just focusing on those weights. Now, the angular momentum, L1, it's I1 times whatever the spin rate number 1 was, omega 1. All right, that's lowercase Greek letter omega. Now, that's just the definition of spin angular momentum. We haven't done anything fancy with that, but, whatever it is, we're going to have that. Now, when she brings her arms in at time T equals T2, she brings her arm, she dips them in close. And, okay, MR squared is smaller. And that means that I2, the new moment of inertia for rearranged distribution of mass, is smaller. Because she's got some MR squareds that used to be out here at big R, and now they're in here at smaller r. So she has that big wingspan, like Mo Bamba. You should see that? Mo Bamba for the Orlando Magic, 7 foot 10 inch wingspan. Unbelievable. So Sierra's out here with about, like maybe 0.7 meters left and 0.7 meters right, and 5 pounds, so that's about 2 point something kilograms. So you can figure out MR squared for her hand weights. And then MR squared down here, when she's in here, when she dips her arms inward, her R, or the R of the two dumbbells, is like about maybe 7 or 8 centimeters, so quite a bit smaller. And so MR squared is going to be smaller. So I2 is smaller, but L2 is, whatever else, it's the product of I2 and omega 2. Now, here's the kicker. And this is what Sierra was demonstrating. She was demonstrating the conservation of angular momentum. Now, that means without any external forces like friction, so she was on a nice turntable that wasn't losing a lot of spin to, friction. It had really good ball bearings. And they make this turntable specifically for that. If that's the case, then L1 and L2 are going to be the same, even when you rearrange your masses, which is what we did. So the spin rates, omega 1 and omega 2, if I1 and I2 are different, omega 1 and omega 2 are going to be different because they have to multiply out to the same number. So if you had 10 kilogram meters squared per second beforehand for your two weights, you're going to have 10 kilogram meters squared per second afterwards for your two hand weights. All right? And that means if I1 is larger so here's I1, hand weights all the way extended. Omega's got to be smaller. Omega 1 has got to be smaller. And if I2 is smaller, then omega 2's got to be bigger because they have to multiply out to the same number. I1 omega 1 have to multiply out to I2 omega 2, no matter how you redistribute. Unless you got some forces. And I changed, and you notice at the end, Sierra and Joseph, at the end, when they came to a stop, I just told them to put their feet down. And when I wanted to stop the bicycle wheel, we just kind of rubbed it with our a little friction, so we absorbed a little bit of the spin. But absent them putting their feet down, they're just going to keep going the same spin rate. It just depends on where the distribution of matter is, out here or in here. Sierra?
I was wondering, do some people have like a better balance with the spin table than others, or like you're really balance?
The question was, do certain people have better balance? The answer to that is yes. And you can't, it's like some people are better dancers, or better at ice skating, or skateboarding, or skiing, or, water skiing. Did you ever go water skiing? Yeah, so if you go water skiing, you got to really have good balance. I mean, you got to have a lot of good stuff, but balance for sure. Whereas playing basketball, you don't really need balance a whole lot. You just, got to jump up in the air and stuff. But yeah, I mean, it depends. So some people will puke and some people won't, So you did good. And Joseph did, although Joseph was getting there. He was getting to the borderline there. I don't know. I think we got him off there. Anyways, this is the ice skater effect. If the weights come in, smaller I1 or smaller I2, omega 2 goes up. If the weights go out, you slow down. Because your angular momentum is in your distribution of matter, not in your spin rate. Okay? So the ice skater effect. Now, I'm going to ask you some more questions here concerning the bicycle wheel demonstration. All right, so let's think about the change in L, the change in the angular momentum. That's what I want you to think about. All right. And this question is, I want you to read it really carefully. So this is about Joseph and Joseph's demonstration. When Joseph, so initially Li subscript Is, that's the initial angular momentum of the student, Joseph, he was at rest, so you got goose eggs there, double goose egg, all right? But the wheel doesn't. The wheel starts, Liw, initial wheel angular momentum is, I just gave it a positive, positive 20, just to give it a good round number. And then when we flipped it, it went down to minus 20. Upside down, same size, good ball bearings, but upside down, so minus 20. All right, so how much must the student acquire? In other words, how big is his delta L? Do you remember what his angular momentum was? Was it upward or downward? Okay, go ahead and answer. And talk to your neighbors and consult and inspire your neighbors. Or just kind of use, no, not your left hand. I saw you. No, behind you with the greenish blue shirt. I saw this up here. Oh, okay. You were faking me out. It's all right. Good. I see people going around like this and stuff. Think. And you know what? This is thinking, and it's a multiple choice question. And I could write 50 multiple choice Scantron questions that would cause a grad student to cry for their mama. So if I make easy calculations in the iClicker part, I might put brain burners in the multiple choice part. Just like this one. Let me see what we got here. Ah. 30 seconds. Twenty seconds. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Come on, you guys. Come on, you guys. Make a decision. Come on. Okay, you're slacking. 4 people aren't clicking. That's all right. You don't need to have an A. That's not a necessary thing in life. Now, I'm going to show you your results. I want you to see this. We are all over the map. 20, minus 20, 40, minus 40, and some zeros. Actually, hardly anybody's voting for negative, 12. That's still a good fraction. 6%. And guess what? If you voted C, raise your hand if you voted C. Nice. Very good. All right, now let's work out why C is the correct answer. I mean, you can see it from this picture. The wheel goes from 20 to minus 20. The final is minus 20, the initial is 20, positive. My wonderful students, this is Jill from the physics department. She's our new assistant for helping out with demonstration equipment. So she'll be here from time to time. And Jill, it went great. So thanks for helping me this morning. So the final is minus 20, the initial. So it's always finest minus initial. So it's minus 20 minus regular 20. That's a total of minus 40 for the bicycle wheel. But the wheel, the student acquires just the opposite. So if the wheel gets minus 20, here's the calculation if you want to jot it down. So you can, the picture allows you to figure it out for the wheel. And the student just gets the same number, but it's up. Because Joseph started spinning like this. I asked you guys, Did he have positive? Did he have upward or downward? Somebody in the fourth row said the opposite of the correct answer. But yeah, he was always take notes when we're doing demonstrations and stuff. So the student in the wheel demonstration, they're exchanging plus or minus delta L. And Joseph, the man who did it, has a question. Go ahead.
Can you go back to the last slide? Because I snapped the picture right as you were switching.
Dude, it's in YouTube. It's going to be in YouTube. Yeah, you got it now? There it is. Is that what you want? Okay. All right. So Joseph and the wheel exchange, just like Rachel and, who was the, Rachel. Who was the other one? The other skateboarder? Who was the other skateboarder with Rachel? Sawyer, or no? It was you? Okay. You're Sawyer? Yeah, Sawyer. Okay, Sawyer and Rachel, they were up here, and they each got equal delta P's, but one was left and one was right. One was positive, one was negatory. Same thing with angular momentum. In fact, there's an exact correspondence. So here's 3 sets of formulas, one for translational momentum concepts and one for rotational momentum concepts. So definition of translational momentum, just P equals mv, v being the translational velocity, the point A to point B velocity, certain direction, certain speed. Omega, L equals I omega, that's the angular momentum, and I is the moment of inertia. It's the exact analog. I is the rotational analog of the mass. But it just depends on the distribution. It's got all those r squareds in it. And omega is the angular velocity, so that's like the RPMs, revolutions per minute. And it has a direction. But, the spin, it's not really going from point A to point B. It's just looping back around. So the actual vectorness is perpendicular to that plane. Force, net force, the second equation block. On the left, F equals delta P over delta T. Yeah, that's Newton's second law. And right next to that over here, tau equals delta L over delta T. That's the rotational analog of Newton's second law. F equals ma, that's the same as F equals delta P over delta T. And here it is for rotate. So the torque is the change in the angular momentum per second. And leverage comes in here on the torque side and everything. And there's a whole lot of trig to figuring out torques and stuff, but basically torques are the things that, here's another way to put it. When I wanted to slow down the bicycle wheel, I put my fingertips in contact with the wheel, with the tire part of it. I didn't, holding on to the sprocket or holding on to the axle up here, high and low, that doesn't have any effect on the spin rate by design. But no matter how many newtons I try to press with that, I'm not going to slow it down. Not very much. But out here at the edge of the wheel, yeah. So the torque depends on where you apply the force. Now the coolest part, and this is new for us, is the kinetic energy. Now we know for translational motion, from point A to point B, the kinetic energy is 1/2 mv squared. We studied that last week. All right? And, that's response to the gravitational potential energy and all that stuff. Now, force, the rotational analog, it looks almost identical. 1/2 I times omega squared. So again, I is in the position of the rotational analog of the mass m. Omega squared is in the rotational analog position of translational v squared. All right, so, and it is not an accident. There are profound physical reasons. Matter of fact, I'll just mention one. The entire theory of relativity can be thought of, or the starting point of the theory of relativity can be thought of as a rotation, a special kind of rotation. Now, in our classroom, the bicycle wheel, I had the bicycle wheel, pretty much parallel to the ground. Now, if you think of the ground as XY graph paper, x-axis and y-axis, then you would say that the bicycle wheel, the rotation of the bicycle wheel is in the XY plane, or parallel to the XY plane. The theory of relativity, however, studies rotations not in the XY plane, but in the XCT plane, the XT plane, a rotation in space-time. And it looks completely different. And all the cool effects, like time dilation and black holes, stuff like that, curvature of space-time, the starting point is rotations in time, space, instead of two spatial dimensions. And there's a lot more that we could talk about, but for now, that's enough. Now, after exam 2, we are going to start applying momentum and kinetic energy and stuff, potential energy, to the idea of heat. That's chapter 6. So your homework after Tuesday, after the exam, will be to start reading in chapter 6. But for now, get ready for exam 2. And we'll dismiss early. If you have a question, you can come on up here. We have some time before the next class comes in. Jill, are you good? All right.